Everyone, and welcome back to the channel. Today, we're tackling one of the most ambitious DIY projects yet. We are going to build a television from scratch, right here at home. Now, before we dive in, let me be clear, this is an advanced project. It involves electronics, high voltage, and a lot of patience. This isn't about saving money. It's about the incredible journey of understanding how a technology we use every day actually works. So, if you love a good challenge and want to learn a ton, you're in the right place. Ready? Let's get started. First up, let's talk about the heart of our television, the cathode ray tube, or CRT. This is the classic, old-school screen technology. Finding a bare CRT can be tricky, but you can often salvage one from an old computer monitor or a small, non-working television. Please be extremely careful when handling a CRT. The neck is fragile, and the tube itself holds a very high vacuum, meaning if it breaks, it can implode violently. Also, the internal components can hold a dangerous electrical charge even when unplugged. Always discharge the CRT safely before you begin. If you're unsure how to do this, please look up a specific guide for your model. Safety first, always! Once you have your CRT, you'll need a collection of other essential components. The most important is the flyback transformer. This is what generates the extremely high voltage needed to power the CRT. You'll also need a deflection yoke, which is the set of copper coils around the neck of the tube. This yoke is what steers the electron beam to draw the picture. We'll need a power supply, transistors, capacitors, resistors, and a good amount of wiring. I've put a detailed list of the components and a schematic diagram in the description below. It's crucial to follow the schematic closely. Now, let's start with the driver circuitry. This is the brain that tells the CRT what to do. We're going to build our circuits on a breadboard first to make testing and adjustments easier. We'll build two main circuits, the horizontal deflection circuit and the vertical deflection circuit. The horizontal circuit is responsible for moving the electron beam from left to right, and it's driven by the flyback transformer. This circuit operates at a high frequency, around 15 kilohertz. The vertical circuit moves the beam from top to bottom at a much slower rate, typically 60 hertz. Together, these two movements create what's called a raster scan, the familiar pattern of lines that fills the screen. Let's focus on the horizontal deflection circuit. This is where the flyback transformer comes in. We'll set up an oscillator circuit to drive a power transistor, which will switch the current to the primary coil of the flyback transformer on and off very rapidly. This induces a massive voltage in the secondary coils where, talking thousands of volts. This high voltage is what accelerates the electrons from the cathode at the back of the tube toward the phosphorescent screen at the front. The deflection yoke, connected to a separate winding on the flyback, will generate a changing magnetic field that sweeps this beam horizontally across the screen. Next is the vertical deflection circuit. This one is a bit simpler. We'll build a sawtooth wave generator. This circuit creates a signal that slowly increases, causing the deflection yoke to push the electron beam down the screen, and then quickly resets, snapping the beam back to the top. When we synchronize this with the horizontal sweep, we get our full screen graph. Getting the timing, or sync, between the horizontal and vertical sweeps is critical. If they're not in sync, the image will tear or roll. We'll spend some time tweaking the resistor and capacitor values in our oscillator circuits to get this just right. Okay, circuit building time. Let's start placing our components on the breadboard. Follow the scheme. We'll connect the power supply, our oscillator for the horizontal circuit, the driving transistor, and the flyback transformer. Remember, we are dealing with high voltages here. Be methodical. Double check every single connection before you apply power. Use a variable power supply and start with a very low voltage to test for shorts or other problems. Slowly increase the voltage while monitoring your circuit. You should be able to hear a high-pitched whine from the flyback transformer once it's running. That's the sound of 15 kilohertz. And it's a good sign. Once the horizontal circuit is working, let's build the vertical one. Again, we follow the schematic to build our sawtooth wave generator and the amplifier to drive the vertical coils of the deflection yoke. Once both circuits are built on the breadboard, it's the moment of truth. We will carefully connect the high voltage output to the CRT's anode cap and the deflection yoke to our driver circuits. When we power it on, if everything is correct, we should see a raster on the screen, a lit up rectangle. It might be distorted, too bright, or off center, but just seeing it light up is a huge success. Now for the fun part, calibration. Using potentiometers in our circuit, we can adjust various parameters. We can change the horizontal and vertical size to make the raster fill the screen. We can adjust the linearity to make sure the picture isn't stretched or squished. We can also adjust the focus and brightness controls, which are usually connected to specific pins on the flyback transformer. This step takes a lot of tweaking. Be patient. Small adjustments can make a big difference. Our goal is to get a stable, well-defined, and evenly lit rectangle on the screen. So, we have a raster. But how do we get a picture on it? We need to modulate the electron beam. This means varying its intensity to create bright and dark spots. To do this, we need a video signal. A standard composite video signal is perfect for this. You can get one from an old DVD player, a game console, or even a Raspberry Pi. This signal contains the picture information as well as the sync pulses that tell the TV when to start each horizontal line and each vertical frame. We need to build one more circuit, a video amplifier. This circuit will take the composite video signal, separate the sync pulses to synchronize our deflection circuits, and use the brightness information to control the electron gun in the CRT. Connecting the video signal is the final step. We feed the sync pulses from our video amplifier to our horizontal and vertical oscillators to lock them in place. The actual video part of the signal will